Alright, here's an updated calendar, just because with all the cancellations and delays and the pep rallies and things we've had, I did want to just give you an updated one. So hopefully you've all watched the 7.1 video. Everyone should have all the worksheets at this point. And so in class on Monday, which will be the 23rd, we'll work on the 7.1 homework, and Monday night you'll be watching 7.2. And then we're again going to work on that in class and kind of review all of those things on Wednesday the 25th. I may change it up a little bit and cut that review day out depending upon how things are going. If we seem to have it after 7.1 and 7.2 days, I'll cut that review day out. And that'll kind of give us an extra day as well. But just everything has stayed the same at this point except for the dates. So I just wanted to give you guys access to an updated calendar, so kind of change your dates on that. Everything's really like 5 days back, with the weekend included and everything else. So try to get that up to date, and we'll see if we last this long. Alright, so today we are talking about section 2, which is inverse functions and relations. And I'm pretty sure we've all talked about this at some point or another in my class, specifically in Algebra 1. Inverse functions, those are just where you switch back and forth between the x and the y values. So it's pretty straightforward. So we'll just go through some examples of how to find the inverses and how to determine whether two things are inverses. And we kind of talked about them with matrices, and it's the same idea. So just what an inverse relation is a set of ordered pairs obtained by reversing the coordinates of each ordered pair. So the domain becomes the range, and the range becomes the domain. So all you do, so I gave you an example there of a coordinate. Started out as 5, -6, and when you switch it and make it the inverse, it's now -6, 5. And that's all. So if you're given a set of coordinates, that's all that you do. It's as simple as that. And obviously, it's not going to stay that simple, but that's where we'll start for now. So they give us this relation. They want us to give the domain and range of the relation and the inverse relation. So let's go ahead and go through. First off, I want to give the domain just of the relation as it is. So the domain, remember, is just all of your x values. So we're going to have 1, 5, -9, and 3. Then the range of that relation is just going to be all the y values. -3, 3, 4. Remember, we don't have repeat values, so I just leave it out. So there's only 3 different values there. Then it wants the domain and the range of the inverse relation. So all I do now is I'm going to mark this as domain of inverse. It's now just our range, or what the range was. So it's -3, 3, and 4. And then the inverse range is just going to be 1, 5, -9, and 3. And you can put those in numerical order, but you don't have to. That's as simple as it gets. So when we have inverse functions, they are inverses if when you switch them. So when we know that they're inverses, if you can put in the domain into the original and get out the range, and then if you put the range into the other, you should get out the domain. So they should work backwards of one another. So for the first one, notice I put in a 5 and I get out a 7. When the inverse relation, I should be able to put in a 7 and I do get out a 5. So that means those two are inverses of one another. So they want us to find the inverse of f of x equals x plus 6 over 2 and then graph the inverse. So in order to find the inverse, there's a few steps here. The first one, we start by rewriting f of x as just y equals. So I'm going to write this as y equals x plus 6 over 2. So all I do is change f of x to y. Now I'm going to reverse the x and the y. I'm just going to switch them around. So it's now x is equal to y plus 6 over 2. and I solve for y. So I'm going to do this algebraically by multiplying both sides by 2. So these will cancel. We end up with 2x is equal to y plus 6. Then I subtract 6, so I end up with 2x minus 6 is equal to y. That's my inverse function. So now I can set that equal to f inverse of x. And then they want us to graph it. Well, that's just a linear equation. I can graph it starting at negative 6. 1, 2, 3, 4, 5, 6. And I go up 2 over 1. Up 2 over 1. And that's my inverse function. So again, the steps, I'm just going to jot them down here for you. We replace f of x with y. Switch x and y. 3. Solve for y. So there's just 3 steps there. You replace f of x with y, you switch the x and the y, and then you algebraically solve for y. Let's go ahead and take a look at another one of these. So I'm going to leave those steps up there and erase my graph. Okay. So find the inverse of f of x equals x minus 3 over 5 and graph the inverse. So again, we have, I'm going to replace that and make it y equals x minus 3 over 5. Switch the x and the y. So I have x equals y minus 3 over 5. And then we algebraically solve for y. So I multiply both sides by 5, so those will cancel. I end up with 5x is equal to y minus 3. Add 3, so I get 5x plus 3 is equal to y. And we're back to graphing linear equations, which I know you guys are probably relieved with this after the things we've been graphing. So again, we start up here at positive 3. I could go up 5 and over 1, but that's going to kind of take me off the graph. So I'm going to go down 5 into the left one. I could do that actually again. And that'll give me my graph. Again, that's all that's to it. Okay. So if you remember with matrices, when we talked about inverses, we also talked about identities. And so with identities, all that means is we can take the composition of two functions, and if they get us the identity, which for this time is no longer the matrix 1, 0, 0, 1, it's going to be just the letter x. So if we can cancel out everything except x, then we know they're inverses of one another. We can determine whether they're inverses if the composition is just x. And that goes both ways. So if f of g of x is equal to x, and g of f of x is also equal to x. So they want us to determine whether these two are inverse functions. So we're just going to go through, and we're going to go f of g of x first. So that's f of g of x, which if you'd rather see it this way, you can write it this way as well. Same thing. I'm going to put g of x in here, so we have f of 1/5 x minus 2. And now I put this into my f function. So we're going to have 5 times 1/5 x minus 2 plus 10. And I'm hoping to get just x. So 5 times 1/5 x is just x. 5 times negative 2 is negative 10. Plus 10 it just equals x, which is exactly what we want. Now let's go the other direction. So let's say g of f of x. Again, you could write it this way as well. So g of f of x, and have g of 5x plus 10. Plug this into that. So we're going to have 1/5 5x plus 10 minus 2. So 1/5 times 5x gives me just x. 1/5 times 10 is 2 minus 2, and again we get just x. And since those are both the identity function, we can determine that they are indeed inverse functions. Alright, this might be one of those times where you want to pause the video and go ahead and try this on your own. Not naive, I know most of you will probably not do that. Because you're just like, why stop it when you can just watch me do it? But I do encourage you to stop the video, try this one on your own, see what you come up with, and then come back, watch the video, and see if you agree with the answer that I got. And again, we're taking f of g of x and g of f of x. So I have f of g of x is going to be equal to f of 1/3 x plus 4. Plug this into my original, or to the f function. So we have 3 times 1/3 x plus 4 minus 3. So 1/3 x times 3 is going to be 1x. 3 times 4 is going to be positive 12. Minus 3, we get x plus 9. That is not the identity function, so these are not inverses of one another. They're not inverses because we do not get the identity function. Alright, so we have one more thing to talk about here, and it's one-to-one functions. What a one-to-one function is, if you remember, a function is just when none of the x values repeat. A one-to-one function, in brief terms, is just when the y values also do not repeat. So if the y values and the x values are all different, then it's not a one-to-one function. Or it is a one-to-one function, excuse me. What that technically is telling us is that the inverse function is a function. So, similar to the vertical line test, we can use the horizontal line test on a function to determine if the inverse is a function. So if it passes both the vertical and the horizontal line tests, then it's a one-to-one function. So we'll go ahead and take a look at an example of a function and determine if it's one-to-one. So you should have a blank graph on your paper, so go ahead and draw this graph with me. So we're going to go ahead and look at the cubic graph, which looks something like this. Now, if I look at the vertical line test, it passes, right? This is a function. So it is a function. So let's go ahead and look this time at also the horizontal line test. If I look at the horizontal line test, going this direction, it also passes. So this means it is a one-to-one function. It's not just a function, it's specifically a one-to-one function. Now, an example of something that would not be a one-to-one function would be a quadratic. Because if you were to look at this one, it does not pass the horizontal line test because it crosses in multiple points this way. passes the vertical line test, but not the horizontal line test. And that wraps up section 2. You'll be working on page 395, 11 through 27 odds, 30 and 31 in class. So be sure to have all the notes and everything with you. And remember, we are going to be having a pop notebook quiz sometime soon. So be sure to bring all of your notes that we've done on these videos with you each and every day.